Right? Can you hear me? So my talk is between you and lunch, so I'll try to be quick here. I'll take an hour or something like that. I'm just kidding. It'll be fast. So first of all, thank you very much, Dr. Panda, for the invitation. I'm very glad to be here. So what I want to present today is the Reinit interface, which is a new interface that is posted for handling failures in MPI applications. And this is a collaboration between Lawrence Livermore National Laboratory and the MVAPICH group. And a lot of this work is done by Saurabh Chakraborty, who is sitting here, and is a student at Professor Spanda's group. So what I want to do is, before I start giving you details of the interface, is to give you some idea of what is the background behind this, why we're doing this research, what is the motivation behind this. And so since this is on the topic of fault tolerance, I want to give a quick overview of what are the current solutions for fault tolerance in HPC applications. And the way I like to see it is that we have essentially three groups or three classes of fault tolerance solutions for HPC clusters. So the first one is what I call hardware level solutions. So here we have essentially hardware duplication, parity, ECC, and techniques like that. And so the idea is that with these mechanisms, we are able to handle errors and faults in the hardware in a way they are not propagated to the system, they are not propagated to the MPI library or the applications. The advantage is that it doesn't require changes in the applications and the system, but it can be very expensive. In particular, it can consume a lot of power if we are duplicating components in the hardware. The second group of solutions is what I call system level solutions. And examples here are system level checkpointing, message logging in the API library, and things like that. So these approaches don't require changes in the application, but again, we could have a lot of overhead because essentially we are in many times replicating state that is not needed for recording from a failure. And then the third group is what I call application level solutions. And so here we have ABFT, checkpoint restart, and in particular, MPI fault tolerant programming models. And this is the focus of this research. So we want to enable new programming, fault tolerant programming models for MPI applications, because at the level of the application has a better view of what can be tolerated, what has to be saved, what has to be recovered from a failure. So, and when we look at the previous work in this area, we've seen that there are several fault tolerance programming models that have been proposed for MPI. The first one was probably the starfish system, which was basically proposing the idea of shrinking recovery, where you have a failure in a process, you can continue with P-1 processes. And then we've seen several techniques in ways to handle fault tolerance that has been proposed in the MPI forum, for example, FTMPI, and recently ULFM, and then on top of ULFM we have Phoenix, and then FAMPI. In addition to this, there are several paradigms and features of these techniques, including whether they do global recovery or local recovery, or shrinking versus non-shrinking recovery, forward versus backward recovery, whether they use the profile interface or not. And the question is, how do we actually group these techniques, how we actually classify them in a way we can understand them, in a way we can actually present these techniques to our code teams, because ideally what we want is to organize these techniques and present them to our scientific developers so they can actually use this in applications, right? So we came up with a classification of the current approaches, and we basically found that we can group them in three classes. So the first one is the most simple approach, is what we call error code checking. So essentially, for each MPI operation, you check if you have an error, and if you have an error, then something has to be done, right? Some recovery action has to be done. So this is the simplest approach you can take. Then instead of, so the second class is what we call try blocks. So instead of protecting every MPI operation deprogrammers protects groups of operations. And if you have a failure or an error in any of these operations, then some action has to be taken. And then we have a third class, which we call full restart models. And in this case, the programmer says, well, I'm not going to protect every operation, every single operation, or I'm not going to do it for groups of operations. But what I'm going to do is that if I have a failure, I will restart the application. So I will treat all the MPI calls with the same way. And what happens is that if we have a failure, the full MPI library is restarted, and then the application restarts from a particular point, which is essentially in the main function. And we can say that we can quantify or group these methodologies by what we call the granularity of detection or granularity of control. So essentially, in the first approach, we have fine granularity because we are dealing with particular or all the MPI calls. And the second one, we have a medium granularity, and the last one, we have a coarse granularity. And what we found is that for approaches that use the fine space, the fine granularity space, the complexity of using these programming models in MPI applications tends to increase. So it's more complex. So when we take these classes of programming models for fault tolerance and present these to our programmers, and when we also talk to other scientists in other labs. So the question, so the main concern is, what is the programmability and usability of all these techniques for fault tolerance? So the questions we get are, how many changes do I have to do in my application to use this? How much time will it take me to actually adopt these models in my program? Will this be better than checkpoint restart? Because most of the codes in production have been using checkpoint restart. So they want to know if adding some of these programming models will be actually better than that. But how do we actually measure programmability of a programming model? In particular, a fault tolerance programming model. So that was one of the questions that we had. And we didn't find a particular way to measure programmability or usability. We started with the simple approach, which is lines of code. Right? So you take an application, add fault tolerance code, and then measure the number of lines. But that's very subjective. Right? So lines of codes are not necessarily a good reflection of the complexity. We could have used, for example, number of files modified, or the time spent in modifying the code. But again, that's subjective. It depends on the experience of the programmer and things like that. So after looking for metrics, we found a metric that is actually used in the software engineering domain, cyclomatic complexity, which we thought was very useful in actually measuring the complexity of the fault tolerance programming model. So cyclomatic complexity has been proposed for many years, so it has been used in the software engineering domain. And essentially, it has been shown, so there are studies that show that programs with high complexity have higher rates of bugs. Programs with high complexity are more difficult to maintain, more difficult to test. And in fact, this has been adopted in the NIST structured testing methodology. So let me give you an idea of how we use this metric, what this metric means. So if I give you a program with 10 lines, and in one program we have 10 assignments, and the other program we have 10 if conditions, which program is easier to understand? Well, the first one, right? Because we only have one execution path here. In the second one, we have more than 1,000 execution paths. So cyclomatic complexity basically measures the number of decisions in a program. And basically using this formula, number of decisions plus 1. So if I want to calculate CC for the first program, it will give me a value of 1. If I want to do it for the second one, it will give me a value of 11, because I have 10 decisions plus 1. And it turns out that there's a recommended value for cyclomatic complexity in the software engineering domain of 10. So currently, studies have shown that if your functions have a cyclomatic complexity of 10, then you have a reasonable way of testing that function, maintaining that in general. So if you go beyond 10, then that's bad. Lower than 10 is good. So we use this then to measure the complexity of the models that I presented before. And let's take an example using the error code checking, the first approach that I mentioned. So here I have a simple refinement loop, basically using just an MPI called MPI already. And then using the error code checking method, we use basically add fault tolerance to this loop using the ULFM interface. So ULFM actually implements the error code checking approach. So you can see that there are a lot of additional conditions that come up out of the fault tolerant version of the loop, right? So this increases the cyclomatic complexity from 2 to 11, so it's an increase of 6. Now the question is, what is the complexity of our MPI applications, right? So if the current MPI applications, if the complexity of the current MPI applications is small, then we don't really care about adding maybe 6 in terms of complexity when we add fault tolerance. But if it's already high, then it doesn't make sense, right? So we wanted to see, taking a large number of MPI applications, what is the cyclomatic complexity of these applications, and whether we are in any of these cases. So the ideal case would be where cyclomatic complexity for MPI applications is small, and then when we add fault tolerance, we are still below 10, which is the recommended value. Or if we are in the acceptable case, right, where we are kind of like in the border. These two are the bad cases and the horrible cases, right? So what we did was to take a bunch of MPI applications and measure the average cyclomatic complexity in functions. These are we did it on MPI on functions that use MPI calls, communication calls, because essentially this is where you would add fault tolerance code to handle errors. And so what we found is that a large numbers of these applications. So here I'm showing essentially the average cyclomatic complexity for the functions where we have MPI calls and the application, and then the red line is the recommended value. So more than 77% of the applications have already high complexity. So MPI applications are actually very complex already. So adding or using fault tolerance programming models that increase the complexity doesn't make a lot of sense for us. Mostly because our code teams would not adopt these techniques because they already have a large complexity. So essentially what we found is that the models that are in the fine or medium granularity of a high complexity, so we don't want to focus on that area. So what we want to do is to propose solutions for this area where we have the full restart model, in which we have basically a small number of changes in the application. And so this kind of fault tolerant programming model can actually be used in a large number of applications with minimal changes. And this is why we're proposing Reinit. So the Reinit interface has 4 key goals. So the first one is to provide a simple program interface. And the idea here is to provide support to standard or current fault tolerance approaches, in particular checkpoint restart, because applications already have checkpoint restart code, and so they can actually reuse their checkpoint restart code to tolerate faults in MPI applications. So Reinit also provides a way to, so the idea is that when we have a failure, we clean up the state of MPI, and then what we have at the end is a state that is similar to MPI init. So all the communicators are gone, all the messages in queue are gone. So we essentially have what we have after we call MPI init, which is a single MPI combo communicator. So all the cleanup is done in the MPI library. It's not done in the application. So MPI takes care of cleaning up everything and then restarting everything. We have a close interaction between MPI and the resource manager that gives us fast detection and fast recovery. And also we have a mechanism to clean up libraries, helper libraries. So in the other approaches, if we have an application with a bunch of libraries, helper libraries, then in the libraries, we also have to add fault tolerance code to handle the failures. So we don't want that. So here I'm going to give you a short description of the interface. So essentially what we have is a set of states that a process can have. new, restarted, or added. And then we have a signature for what we call a reinitialization function. So this is the function that actually performs all the work in the application. So we also have cleanup handler signatures, and then functions for essentially push and pop cleanup handlers. So the idea is that when we have an error, we want to mimic what happens in C++ with try and catch, where you have a hierarchy of error handlers that take care of cleaning up the state of the application and the library. Right? And so this is an example program. So essentially, in the main function, we have MPI init, then we have we push the cleanup handlers, and this is done by the application and by any library that is supposed to be running on this application. And then we have the Reinit function, which is defined here, and this is where everything happens. This is where the recovery using checkpoint happens. This is where the actual computation of the application happens, and where the checkpoints are stored. So basically, we are replacing main by the resilient main here. So this is a short description of the workflow of Reinit. So say we have 4 processes, and we have a failure in process 3. So what happens is that we have an out-of-band notification to all the other processes. So process 3 goes into a restart mode, wait for the others, then the other processes basically do a finalize and MPI initialize. And then at the end we have the first 3 processes that did not fail in a restarted state, and then the process 3 on an added state, because we have to add this process after the failure. Now we're doing, so we most of this work in terms of detecting the failure and things like that is done on the Slurm resource manager. So there are a lot of things that happen at that layer as well. So here I have showing how we have failure detection in at that layer in the resource manager. So we have the hierarchy of SRAM daemons and MPI process here. So if we have a failure in process 0, what happens is that there is a notification to the Slurm, the processes that handle that MPI process, right? And then that process notifies the main SRAM process, which then broadcasts information to all the other processes to allow the reinitialization of the MPI library. So we have done some experimental evaluation of Reinit. So we're working right now. So the results that I'm going to show are basically for the single process failure scenario. So right now we can handle single processes failures. So we're working on the non-failure case. And we've done this at clusters at Lawrence Livermore. So here what we're showing is basically the recovery time for using Reinit and the traditional approach of restarting the job. And as we can see, in less than 4 seconds, you can recover with more than 1K nodes. So this is much faster than restarting the job, which is the actual technique that programmers use. And here we have the time when we compare Reinit with job restart. But here we are storing a checkpoint of 100 megabytes, and we're storing this checkpoint in memory in adjacent processes. So we have the advantage that since the job is not killed, we can restore the checkpoint that is stored in memory from another process. In the job restart case, we lose the memory, so we have to read the file system. So we are doing much faster, of course, than a traditional job restart. So in summary, so the programming complexity of fault-tolerant programming models can be an impediment for adopting these models in large applications. So we want to provide solutions that reduce the complexity and reduce the amount of time that programmers spend on using these models. So we are proposing Reinit as a low programming complexity interface, and that supports, so this interface supports current practices in fault tolerance, such as checkpoint restart. There's a close integration between MPI and the resource manager, and we have simple ways to clean up both the application state and the library states. So we have a current implementation in MVAPICH and Slurm, and as future work, we are working on supporting node failures, and hopefully we can release this code at some point later. And these are all the team members that have been participating in the project. And with this, I'm happy to take any questions.